Okay, balancing chemical equations. So, if you notice that there is a G next to every one of the compounds, the G stands for gas. It's a state of matter. If it was an S, it would stand for solid. If it was an L, it would stand for liquid. The way that we start balancing our chemical equations is we make our list of elements that are in the chemical equation. We have a C here. We have an H. And we have an O. We make our little grid. I know that many people teach making it on the right-hand side or making it on the left-hand side or up above. For me, this makes the most sense. It's the way my brain thinks. I get too confused if it's moved around unless it's directly below. So, we have 2 carbons on the reactant side, and we have 1 carbon on the product side. We have 2 hydrogens on the reactant side, and we have 2 hydrogens on the product side. How many oxygens do we have on the reactant side? 2. And how many on the product side? If you said 2, you forgot to add the extra one over here. Even though it's not listed, there is a subscript of 1 next to any single element in a compound. So I'm just going to put that for our own reference. So we have a total of 2 plus 1 more is 3. So the only thing that's balanced right now is hydrogen. You want to go for balancing the most complex compound in the equation and leave the least complex, the singletons, or the diatomic molecules, for last. Sometimes water is the least complex, so you leave that for last. But in this case, it's the oxygen. So in order to have the same number of carbons on the product side, I have to basically put something here. I have 2 carbons over here and 1 over here. What number times 1 would equal 2? 2. So you put a 2 there. And then we have, so our carbons are balanced. Our oxygens, 2 times 2 is 4. Plus 1 more over here is 5. So then our carbons are balanced, our hydrogens are balanced, but our oxygens are not. So I want the same number of oxygens, and in this case I want them even. It makes life easier. So what number would I put in front of here in order to have an even number of oxygens? Well, I'm going to put 2 in front. So, but now remember the coefficient applies to the entire compound. So 2 times 2 is 4. So now we have 4 hydrogens. We have 2 times 1 is 2, plus 4 more, 2 times 2. So is a total of 6. So my hydrogens and my oxygens aren't balanced. I need to have the same number of hydrogens on both sides. So the way that I do that is I put the hydrogen, what number would I put in front of here to have 4 hydrogens? I'm going to put a 2 in front of here. 2 times 2. So that leaves me with 4. Only problem is this coefficient applies for the entire formula. So 2 times 2 is also 4. So now I have 4. Now I have to change this again. So I'm going to change this again so I have the same number of carbons because I have 4 carbons on the reactant side. I need 4 carbons on the product side. So I'm going to have to put a 4 in front of there. 4 times 1, that gives me 4. 4 times 2 is going to give me 8. But I also have 2 more over here. I have a total of 10 oxygens. So my carbons are balanced, my hydrogens balanced, my oxygens are not. And this is why we leave the singletons, the individual atoms, for last. Because what number times 2 is going to give me 10. So we're going to do 5, and so that will give me 5 times 2 is 10. So at this moment, it is balanced. To read this chemical equation, we can read that there are now 2 moles of C2H2. We also have 5 moles of oxygen. We have 4 moles of CO2. And we have 2 moles of H2O. If you notice, I've put a line between. This is the reactant side. This is your reactants. And this is your products. Now remember, conversion factors, we can flip these around. So if we were going to say I have a mole of 2 moles of C2H2 for every 4 moles of CO2. So 2 moles of C2H2 or for every 4 moles of CO2. We can also write this flipped. We have 4 moles of CO2 for every 2 moles of C2H2. We can also write it mathematically. 2, 2, 4, or 4 to 2. And that's for any element on here. So to figure out how much volume using these, I'm going to erase our balancing grid. And our balancing grid is now going to have, is now gone. And so what we can do is we can, 1 mole of any gas, of a gas, is equal to 22.4 liters. So if that's the case, we have 2 moles of C2H2 is going to equal 2 moles C2H2 over 1. And we know that 1 mole of C2H2, which is a gas, is equal to 22.4 liters. So we can cancel the moles here and cancel the moles here. So then the rest is math. So we can take and multiply 22.4 and multiply it by 2, so that gives us 44.8 liters for 2 moles of C2H2.